Okie dokie. Alright, now, we've set out to prove that the diagonals of a kite bisect a pair of opposite angles. So here's our kite. Remember, a kite has two pairs of sides that are congruent, two pairs of congruent sides, and specifically the congruent sides are not opposite each other, they are next to each other. And they're the diagonals drawn through the center, and up here there is one angle, so ABC is bisected by this diagonal here, and then down here ADC is bisected by the diagonal down here, and that's what we're going to prove. And we're going to prove it using the same kind of method we've been using. We're going to find a pair of triangles, show that those two triangles are congruent using one of our congruence criteria, and then based on that, we'll say, okay, well, if they're congruent, then these particular parts of the triangles must be congruent, and that's going to lead us to this angle bisector bit. So here we go. So first we have that AB is congruent to BC. So that's AB congruent to BC, and that AD is congruent to CD. AD congruent to CD, and that's just given to us. That's what it means to be a kite, basically. Next we have that BD is congruent to itself. BD is congruent to BD. And that's an important fact because that's going to be the third side in each triangle to go with side-side congruence. And if we have to give a reason why BD is congruent to itself, we would say reflexive property. Reflexive property just means that everything is equal to itself. Everything is congruent to itself. So now that we know that AB congruent to BC, BD congruent to itself, and AD congruent to DC, we have the triangle BAC is congruent to triangle BCD. So triangle BAC congruent to triangle parallel triangle symbol there. It's real small now. BCD. Oh, that looks terrible. BCD. And of course, remember, it's important to name them in the correct order. I mean, I could have called this triangle ADB, then have to call the other one CDB. So I have to make sure we name them in the same order so that we know which angles and sides correspond. So now that we know those two triangles are the same, we know that angle ABD is congruent to angle CBD. And we know that angle ADB is congruent to angle CDB. Okay. And so this gets to be kind of a confusing mess. You know, oftentimes have to read it very slowly. How do we know if those two angles or two pairs of angles are congruent? Well, we know they're congruent because they are corresponding parts of congruent triangles. So they're pairs they're sides that match up. If you look here specifically, if you want to think about how does this one match up with this one, it's a reflection. We could just reflect this triangle across this diagonal, and it would match up with the other one. So C would match up with A, B would end up being matched up with itself, D would be matched up with itself, side DC would get matched up with DA, and so on. Okay. And these two angles down here will get matched up with each other, and these two angles up here will get matched up with each other. So they are corresponding parts of congruent triangles. Well, that means that BD bisects angle ADC and angle ABC. Let's look at this closely. BD is the diagonal, and it bisects angle ADC and angle ABC. And how do we know that? Well, we know that because it cuts each of those angles into two congruent parts. And that's what it means to be an angle bisector. If the line cuts an angle into two congruent parts, then it's an angle bisector because that's what an angle bisector is. So because these two pairs of angles are congruent, right, then the segment that creates them must be an angle bisector, because that's what angle bisectors do. They cut large angles into congruent parts. Let's see. Oh, oops. Well, I was going to go and break that into, we don't need that. Okay, and we're done. Now, the other question was, well, what about the other pair of angles? If you look here, it does not appear that these two pairs of angles are bisected. It looks like this side of the angle is a little bit bigger than this one, and in fact it is. So could it be, if there's their case where this diagonal, this one here, would also bisect angles BAD and BCD? Well, yes, there is. It'd be down here if we kind of shortened up the bottom of the kite so that these two sides were also congruent, and then the lower triangle was congruent to the upper triangle, and I could sort of do that reflection thing across the other diagonal. See how this shape here is symmetrical across this diagonal, which means that we can fold this over, which is how we knew that the top and bottom pairs of angles were congruent. But I can't fold it the other direction. I can't fold this B down to D to match it up. It's not symmetrical that way. If it were, if B could be folded down to D, then the top triangle and the bottom triangle would be congruent, which would mean that the angles down here would kind of get folded in half over this diagonal, and then they would also be congruent, which would make this diagonal also an angle bisector. But the problem is, it's no longer a kite now. Specifically, it's included in the definition of a kite, typically, that the opposite sides of the kite are not congruent. Because when you have the opposite sides being congruent, as well as next door sides being congruent, then all the sides are congruent. We call this shape a rhombus. So, and in a rhombus, yes, each diagonal will cut the opposite angles into congruent parts. In fact, all four of these angles here will be the same, and all four of these two and these two, those are all the same. Not all the angles are the same, but the angles at either end of the diagonal are all the same. Either end of this diagonal are all the same. And in the center, they are right angles. That's true of the kite as well, I guess. So it's just a sort of classification thing. Yes, the other diagonal of the kite could be an angle bisector, but if it was, then we would no longer call this shape a kite. We would call it a rhombus.